A $50 roll of aluminum foil stapled to your attic rafters reflects 97% of the heat that is baking your house right now. Your $1,000 insulation can't even come close. NASA solved this in 1959. The fiberglass industry buried it. Three principles of physics explain why. But heat doesn't just move by conduction. It does so in three ways: conduction, convection, and radiation. Convection is heat carried by moving air, like the hot air rising through your attic. And radiation is electromagnetic wave energy traveling at the speed of light, requiring no contact or medium. It's the same energy that warms your face when you're in the sunlight. Now here's the part that changes everything. The Florida Solar Energy Center, a government research institution, measured exactly how heat enters your attic during the summer. Between 65 and 80% of the heat passing through your attic airspace arrives as radiant energy, not through conduction through the shingles, nor through hot air rising by convection. Invisible infrared radiation emanating from your overheated roof deck. Your fiberglass insulation, with its impressive R-value rating, sits beneath all that radiation and does almost nothing to stop it. R-value cannot measure resistance to radiant heat. It was never designed for that. The entire rating system the industry built to sell you insulation literally cannot account for the dominant source of heat entering your home in the summer. You're probably thinking, wait, so what is my insulation actually doing up there? It handles the 20 to 35% of heat moving through conduction and convection. It does that job well. But it is completely blind to the 65 to 80% that arrives as radiation. Think of it this way. Your fiberglass is a sponge trying to soak up a flood. But the flood isn't water, it's light. And sponges don't stop light. This is what most people don't understand. What percentage of the heat entering your house is actually blocked by your attic insulation during peak summer hours? Most people assume 80 or 90%. The real answer depends entirely on the type of heat. Your insulation handles conduction well, but against radiant energy, which makes up most of the summer heat load, it's nearly transparent. The heat passes through, turns into thermal energy in your attic air, and your air conditioner pays the price every afternoon. This is known as the R-value blind spot, and this is where everything the insulation industry told you falls apart. They've taught you that insulation is rated by R-value. The higher the number, the better it works. That's what contractors learn. That's what building codes demand. That's what the fluffy pink rolls in your attic are measured by. But here's what no one explains. R-value only measures one type of heat transfer: conduction, heat flow by direct contact, like the handle of a pan getting hot on a stove. Your fiberglass blanket slows conductive heat excellently. It traps pockets of air that resist heat movement through solid contact. But there is a material that was specifically designed to solve this problem. And the story of how it was buried tells you everything about how the insulation industry protects its $60 billion in annual revenue. This involves the emissivity effect. And this is the most important physics concept your contractor was never taught. In 1959, NASA's Thermal Engineering Division faced a problem no home contractor had ever encountered. They needed to protect spacecraft from a 500-degree thermal swing. It was plus 250 degrees on the sun-facing side and 250 degrees on the shaded side. Fiberglass was useless in space. There's no air to create conduction. The only threat was radiant heat, infrared energy flowing directly from the sun in the form of electromagnetic waves. NASA engineers developed a metallized film, an ultra-thin layer of aluminum, bonded to a reflective substrate. They tested it in vacuum chambers and verified it in thermal model simulations. The result was so effective that it has been implemented in every spacecraft from Apollo onward. The Apollo command module used multiple layers of crinkled aluminized mylar. Inside, astronauts worked in shirt sleeves at room temperature, while the outer hull experienced 500-degree variations. The same material was used in the suits that kept astronauts alive walking on the lunar surface, where ground temperatures reached 260 degrees in direct sunlight. It was inducted into the Space Technology Hall of Fame in 1996. The physics behind it comes down to one number: emissivity. Every material has an emissivity rating between 0 and 1. It measures how much infrared radiation a surface emits relative to a perfect black body. Your roof shingles have an emissivity of around 0.93. That means they radiate 93% of their thermal energy downward into your attic. Wood and drywall are around zero point 0.9. Paint is between zero point 0.9 and 0.96. Almost everything in your house is a near-perfect heat radiator. Aluminum foil has an emissivity of 0.04. It only radiates 4% of the thermal energy and reflects the other 96% back toward its source. That's a factor of 23 times less radiant heat emission than your roof shingles. When you staple this foil to the underside of your roof rafters with the shiny side down, it intercepts the radiant energy before it turns into heat in your attic air. Oak Ridge National Laboratory tested this. Their full-scale climate simulator found that low emissivity foil stapled to the rafters reduced summer heat flow through the attic by 50%. Attic temperatures dropped 30 degrees. Ceiling surface temperatures fell 10 degrees. Think about what that means for your air conditioner. Instead of fighting a 140-degree attic all afternoon, it's managing a 110-degree attic. The Department of Energy confirmed that in Sunbelt states this translates to significant reductions in cooling costs, and the Florida Solar Energy Center documented roof heat flow reductions of 30 to 50%. One homeowner in Phoenix installed 2 rolls one Saturday afternoon in April. His attic temperature the following July measured 104 degrees in full sun. The previous July, in the same attic and same house, it was 138 degrees. His AC went from running 4.5 hours every peak heat afternoon to 1.8 hours. His July electric bill dropped $187 compared to the same month the year before. The total cost of his material was $54. Your AC runs less, your compressor cycles less, your electric bill goes down, and the material that makes it possible costs between $30 and $60 for each 500 square foot roll. This brings us to the thermal saturation trap. And this is the part that keeps costing you money even after the sun goes down. Most people assume their cooling problem ends at sunset. The sun stops hitting the roof. The attic cools off. The AC takes a breather. But that's not what happens. During peak afternoon hours, the roof deck absorbs massive amounts of thermal energy. That energy radiates into the attic all day long. Fiberglass insulation absorbs some of it, and after 8 to 10 hours of continuous radiant bombardment, the fiberglass itself gets hot. It reaches what engineers call thermal saturation. The insulation is so hot it stops effectively resisting heat flow. It becomes a thermal battery. And after sunset, as the roof deck starts to cool, your saturated insulation keeps radiating that stored heat downward into your living space for hours. This is why your house feels stifling at 10 p.m., even though the outside temperature dropped 20 degrees 2 hours ago. The ceiling is warm to the touch because the insulation above it is slowly releasing the thermal energy it absorbed all afternoon. A radiant barrier breaks this cycle at its source. By reflecting radiant energy before it reaches the insulation layer, the fiberglass never gets saturated. It stays cooler all day. It maintains its rated R value performance instead of degrading under the thermal load. And when the sun goes down, there's no stored heat to radiate downward. Nighttime cooling happens in minutes instead of hours. Oak Ridge National Laboratory confirmed this in their controlled studies. Homes with radiant barriers showed drastically faster nighttime temperature drops because the lower insulation layer never built up the thermal load in the first place. The foil intercepts the radiant load. The fiberglass handles any remaining conduction and convection. Together, they far outperform either one alone. Now, here's the part the insulation industry doesn't want you to consider. In 1991, radiant barrier technology was quietly removed from the major residential building science guide distributed to contractors across the United States. It wasn't banned. It wasn't debunked. It was simply omitted. Updated guidelines spent pages covering fiberglass ER value ratings and gave radiant barriers a single paragraph calling them supplemental. Contractors trained on those guides never learned how to install them. Homeowners never knew to ask for them. A multi-billion-dollar industry ensured that the one product that could replace their recurring revenue model with a one-time $50 purchase simply disappeared from the conversation. Installation is simple. Buy perforated radiant barrier foil at any hardware store. Staple it directly to the underside of the roof rafters with the shiny side facing down toward the attic space. Never lay it flat on the attic floor over the insulation. That traps moisture and voids the airspace. The reflection mechanism needs to work. Overlap the seams by about 2 inches. One person can cover an average attic in 3 to 4 hours with nothing more than a stapler, scissors, and a tape measure. The insulation industry built an entire rating system around R value, a metric that conveniently cannot measure the one thing their product fails to fix. They spent decades teaching contractors, building codes, and homeowners that R value is the only number that matters. Meanwhile, a $50 roll of aluminum foil designed by NASA handles the dominant source of heat in every American attic. And most people have never heard of it. If a $50 roll of aluminum foil cutting your cooling bill sounds hard to believe, wait until you see what a $7 powder does to your $3,000 AC unit. The physics is even more brutal. That video is right here. If this story has changed how you look at the hidden technology in your home, please subscribe and like the channel. We are uncovering the history and science they have tried to bury for decades. Let's build a more efficient future. Our next investigation into the secrets they don't want you to know will be published soon.